Hello everybody. Hope everybody has been well. Hope everybody is staying safe and healthy. Um, Weather's been questionable. Some nice days and some not so nice days. So, anyways, hope you're able to get out when you can. Enjoy some of the warmth. Go out for a walk or something. But, anyways, where we are going to pick up with last week, right? We talked about the nervous system. Right, basically that is, again, Cliff Note version, right? For instance, our brain needs to receive a huge amount of sensory information or sensation, right? For instance, as you're listening to me right now, right, little tiny neurons inside of your ear transmit these impulses into the brain, and then your brain can decode those impulses and you hear what it is that you hear. Why is it we touch, or when we touch something, right? As we touch something, we are able to feel it, right? Why is that, right? Well, those are the sorts of things that we covered last week in the presentation. Now, where we kind of left off on was, right, what actually generates these nerve impulses to begin with, right? Last week, right, as I had mentioned, right, what we talked about a second ago, but something else we talked about was kind of the tract or the highway system, that when you touch something, for instance, that entire highway from point A to point B, right, how it gets from, let's say if you touch something with your fingertip, how is it that nerve message or that nerve impulse gets from your fingertip all the way up to your motor all the way up to your primary somatosensory cortex, right? That postcentral gyrus. How is it gets up there, and then what happens as a result of it, right? The motor component, that the motor cortex, right? The precentral gyrus, the initiation of that movement, all of that takes place at the motor cortex. So that's what we had finished up on, right, last week. But when we think about what actually generates that action potential, or what generates that nerve impulse. Okay, so I had mentioned how you touch a table, right? And that when you touch a table, that stimulates little tiny touch receptors or touch detectors in your fingertip. But how? How is it that it actually stimulates them, right? And that's where we're going to get in with today. So again, example here, you touch something, let's get a pen going here, where you touch something, touch a pen, so this little tiny touch receptor here in your finger is stimulated, alright, and that sends that nerve impulse up the hand, into the arm, forearm, eventually into the spinal cord. Right? From the spinal cord, it makes its way all the way up to the primary somatosensory cortex. Cool. Well, that had to begin way down here. Right? Let's just imagine if I could just erase this receptor. Would you feel anything right here in your fingertip? No. You think that sounds awful? Yeah. If you've ever had any sort of surgery or any sort of injury where you've had kind of long-standing kind of numbness, right? Old school ACL repair, C-section, right? Right. The skin overlying the surgery site, it just has a different feel to it. It almost kind of feels like, kind of just like numb. And the reason why is because the neurons, right, in part those sensation detectors or those touch receptors have been, obliterated. They've been cut through. They've been destroyed. So if there isn't any sort of touch receptor in that area, nothing is going to allow you to permit any sort of sense of touch, right? Now, like in your fingertip is much more sensitive, right? For instance, we can all understand your fingertip is much more sensitive to touch than, let's say, the back of your shoulder or the back of your arm. Right, the back of your arm, right, there are far fewer touch receptors. So because of that, your fingertips are much more sensitive. And it makes sense because we need to be able to carry out very fine, very delicate motor movement in our hands, emanating from our finger and from our touch. So a little bit of a kind of a jump back or a review from last week, right? I wasn't going to, but you know what? Why not? Got nothing but time. So as we stimulate this touch receptor, that nerve impulse, again, as I mentioned, travels up the neuron, enters into the dorsal root, synapses in the dorsal root ganglion, then continues onward. The daisy continues onwards into the posterior horn. From there, it then jumps into the white columns, and then from there, it travels all the way up to the brain. And that was all stuff we covered last week. Now, we see plasma membrane includes chemically gated channels, plasma membrane includes voltage gated channels, plasma membrane includes voltage gated calcium channels. What in God's name? Alright, this is a sensory receptor. Let's just call it touch. Let's call it a touch receptor. REC. Alright, so it's a detector for touch. Awesome. Okay. Now, whereas you can, for instance, just if you're in a room, go over to the light switch and flip it. The light either goes on. Let's imagine you go into a room and the light is off. I want to turn the light on. What do? Go to the switch, flip the switch, right? Old school, right? My grandparents used to have the clapper. The idea. If you're like, some people probably don't know what the clapper is, right? Look it up. It's worth that used to exist. Well, it still exists, but people used to use that thing. And anyways, you go over to a switch and you flip the switch, and that activates the light. Cool, light comes on. Our neurons, our body cells don't have this almighty switch. There has to be something which activates them. There has to be something which turns them on, right? So our cells, our body cells have a charge. And if I don't get that, what does that mean? That means, let's say if I had a voltage meter, right, something to measure, voltage and current. If I then took a voltage meter, let's say I'm drawing one here, antenna, it's got a bunch of numbers on it, If I took both leads, stuck it into this cell, it would have a measurement of around -70. That's something called the resting membrane potential. The resting membrane potential, that is the fancy term for, hey, that's the charge of cell at rest. Right, so when the cell is not active, the easiest example of that is to talk about skeletal muscle. If your arm is just resting on the table, your skeletal muscles are at rest. So their charge is right around -70. And as long as it remains at -70, your muscle cells will not become active. Right? When they become active, that's when you contract. Alright, so make a fist. Alright, I made a fist. Let's imagine you made a fist with your right hand. Alright, if I make a fist with my right hand, the muscle responsible for that is, let's just say, it's only my flexor digitorum. So what does that mean? That means the muscle cells that make up the flexor digitorum are no longer at this charge, because that's their charge at rest. Well, if I just made a fist, they're active. They're no longer at rest. So we're going to go through this stuff and talk about it. But what we need to look at is, alright, well, how to... Let me get some of this. I only took 4 clicks. There we go. Alright, well, how do we get this cell off of 70? Right? If this cell, let's say you touched something. I touched something, oh, this cell now gets stimulated. And it generates a nerve impulse. But how did it do that? It has to do with these gated channels. Alright, so let's think about something this way. Let me see. Yeah, we'll jump there in a second. Let's think about it. Let's just think about math for a second. Ugh. God, don't worry. I promise I will keep it simple. Simple math. Right? Like, well, simple math. I promise. In order for a cell to become active, alright, so if this guy, if this girl, right, this cell wants to generate an action potential, it has to reach something called threshold. Meaning its charge, if its charge is at 70, it's at rest. A cell becomes active or a cell will become active once it hits threshold. That is negative 55 millivolts. Right now, really, actually, I really should have written threshold, not active. And it might be semantics, but I'll explain it in a second. I'll just put thresh. Yeah, hell with it. Threshold. Threshold is negative 55 millivolts. So what does that mean? That means if this cell remains at negative 70, it will remain at rest. It will not do anything. So if I want to make a fist, I won't. If my muscle cells of the flexor digital, let's try that one again. If the muscle cells of the flexor digitorum remain at negative 70, you will not make a fist. We have got to get these cells to cross threshold. What that means is once the charge hits right around negative 55, these gates that we talk about, this is when certain gates just open wide. Just throw the gates open. All right. For what reason, we'll get to that. But let's just think about this for a second. How do I possibly make a negative number reach that? Alright, how do I make it less negative, right? Because if it's going from negative 70 to negative 55, it's becoming less positive. I'm sorry, it's becoming less negative, or it's becoming more positive. How do I do that? Alright, well, what's actually giving this cell its charge? Oh, jeez. Think about that one. Oh, yeah. Let's jump back to chapter 2. Right? We didn't so much talk about it in the lab. But the ions. Remember those little tiny molecules right inside of the cell? Right? Sodium, potassium, chloride, magnesium. Don't remember if I said calcium, but these all have a charge. Some are positive, some are negative. Right? Chloride is negative. do we get this cell from negative 70 to negative 55? Well, hey, you know what? If I add a bunch of positive to it, right, if I added a bunch of positive to this number, negative 70 becomes more positive, and that's what gets me closer to threshold. That's right there. Simple as that. The concept is as simple as that, right? But that's what we're talking about, right? How is it right, when we want to talk about a cell going from rest to becoming active, we have got to influence the ions which are inside of that cell. That is how we influence whether that cell becomes active or remains at rest. That makes sense? Well, when I say that, I'm like staring at the speaker, like anticipating an answer and a response. Yeah, I'm just, it's down in my basement, hearing all sorts of weird noises, but that's okay. I'll just keep on trucking. So, anyways, when we look here, right, chemically gated, voltage gated, there are different types of gates, and there are different types of channels which are going to allow certain ions through. Some allow sodium, some allow potassium, some open for different reasons. That's what we're going to get into right now. Here, we're going to spend about 10 seconds on these ones, because these ones are just the way that they are. There are certain channels which are just designed to allow certain molecules through. For instance, here, the example is potassium. There are just random channels. Some are open, some are closed. Please, for the love of whatever holy being you want to mention, don't say, oh, well, why is that? Because it's random. Some of them are just randomly open, some of them are just randomly closed. Some of them randomly open and close. Right? It's called a leaky channel. Right? So why the hell does my faucet leak? Well, because I'm not a plumber, but sometimes I like to pretend I am one. Right? It just leaks. Alright, moving on. Cool. Here, a ligand gated channel. Ligand is just a fancy word for chemical. Right? Now, there's any number of things can be chemicals. Ions can be chemicals. Right? Neurotransmitters are considered chemicals. Right? In the muscular system, in chapter 10, 11, well, 10 and 11, but it would have been chapter 10 when you learned the physio of it. Acetylcholine is the neurotransmitter which is released from the synaptic end bulb. When that happens, acetylcholine crosses the cleft and binds to the acetylcholine receptor on the muscle cell. When acetylcholine binds, it opens that gate. Think of a chemically gated channel, right? What's the key? Well, the key is the chemical, right? It's not some piece of metal, right? If I am a ligand gated channel, that means you better have the right chemical, or else I'm not opening up. So acetylcholine binds to an acetylcholine receptor, and that particular gate opens. Make sense? Next, mechanical stimulus. Yeah, right. The different touch receptors. This is how they function. Right? Literally, think about it. Take your finger, poke it into the table. Just look at your skin. Look how your skin is distorted. Yeah, as your skin distorts, for instance. Well, as it distorts, that literally changes the shape of the receptor. When it changes the shape of the receptor, that's what actually opens it up. Right? Think about my can opener. I've got two of them, and even combining the two, it's still a hell of a time opening opening certain cans. But when the can's most of the way open, if I just take the can and just squeeze it, the lid pops open. That's what happens with these mechanoreceptors, right? These mechanically gated channels. Literally distortion, actual physical force distorts the shape of the receptor, and that's what causes it to open, just like the can of peas I tried to open up. Right? It was, my can opener kind of sucked, didn't work it too good, but I opened it just enough where if I then squeezed the can, the top popped open. Think of that exact same concept. These here, voltage gated channels. Alright, so what does that mean? Well, whereas ligand gated or chemically gated, there was a chemical key. As long as I had the appropriate key or the appropriate chemical, the gate would open. Mechanically gated channels, right? As long as I have mechanical force, as long as I distort the membrane, or as long as I distort the receptor, it'll open. Right? I could throw whatever chemical I want at this receptor. It doesn't matter. It doesn't care whatsoever. Right? The key for this is mechanical stimulus, is actual mechanical pressure. Here, these voltage gated channels. These are voltage keyed channels. Right? Remember a minute ago how I talked about threshold? Threshold. It's right around negative 55. Threshold's negative 55 because at that point, that's when a whole bunch of ions flood into the cell. Well, this right here is what actually occurs. There are these voltage gated channels. Their voltage key, or their key, has a voltage of right around negative 55, meaning that once I hit negative 55 millivolts as a charge, that's when these gates open. When these gates open, that's what then allows the ion to move through the channel. Right? Does that make sense? So literally think about it as being a key, a voltage key. Right? It's got to be the right voltage in order for the key to work. Alright. So this is, again, right, this is the actual neuron. Right, you can see positive, negative. Right, yeah, there are certain molecules, right, on the inside of cells. Right, proteins. Right, potassium. Right, chloride. And there's different molecules that are negatively charged. There are certain molecules which are positively charged. Same thing with outside of the cell. Right, there are certain molecules which are positively charged, like sodium. There are certain molecules which are negatively charged, like chloride. Outside of the cell, right? So when we talk about the fluid outside of the cell, so like interstitial fluid or plasma, right? Sodium makes up a huge 90% of the ions in that in extracellular fluid, right? The fluid outside of the cell, out through here. Not inside of the cell, outside of the cell. 90% of it's sodium. So, are there other ions like calcium, magnesium? Absolutely. Which one's the most important? I don't know. You tell me. What do you think? Right? If sodium makes up 90%, I'm probably going to bank on the fact that sodium is the most important, and that's why sodium is the one that's always talked about, and the movement of sodium is the most important. Now, inside of a cell, right? Inside of the cell, it's potassium, which is the most abundant. Not quite 90-10, but it's pretty high up there. 80-85% of the ions inside of the cell are potassium. resting membrane, but there we go. Resting membrane potential. Remember, negative 70. Negative 70. Cool. So I've got to get, let's say, a bunch of these positives into the cell. And when that happens, this negative 70 becomes negative 55, and then the floodgates open, and then there's a big, huge swing of a ton of positive molecules flooding into the cell. As they flood into the cell, that's what is referred to as depolarization. Yep. See, I was going to try and refrain from talking and writing. I tried doing it and I had to stop. I can't do it. Right, depolarization. Depolarization, that's essentially the process of generating that nerve impulse. Right, that is the process, but when that neuron, when that cell produces the action potential, when it depolarizes. All right. Woof, mama. All right. Let's look at the cell here. Alright. So, well, the resting membrane potential. Right here is, again, the stimulus. That's when, hey, somebody you just touch the table. Right. So you can see how there's a little slight increase, reach threshold, then there's a big spike here. Then it has to reload, that's called repolarization, and there's the what's called hyperpolarization. Okay. This is, hey, I'm using this as an example, right? I'm using a touch receptor as an example. I could have thrown a muscle cell in here, right? And there's a number of examples of cells that could have used. But the reason I'm using the touch receptor is you'll find out in just a second. Not every single thing that you do generates an action potential, right? For instance, do you feel everything that you touch? You might say, well, yeah. All right. Go find an ant. Right. It's going to be springtime, so this is about the best time of the year to find them. Let one crawl on you. Right. I promise you. Right, unless you're talking about some carpenter ant or some of those kind of, African ants, which are about the size of a cockroach. Right. If it's just a normal, good old-fashioned, run-of-the-mill ant, I can't think of the actual name of the most common small ant breed. I can't think of it right now. But when it's crawling on you, right, if it's not hitting your hair, for instance, if it's not crawling around on the back of your hand, but let's say it's crawling on your palm of your hand or on your fingertips, and your fingertips, they are insanely sensitive to touch. But even if you had an ant crawling on it, I tell you what, you're going to be really hard-pressed to feel it on you. Why? Because even though it's touching you, it's walking on you, it's crawling on you, it doesn't generate enough of a change in the charge of that touch receptor for it to generate an action potential. Right? Because you only feel it if it reaches the brain. Right? If no nerve impulse is sent to the brain, you don't feel it. I can see it walking on me, but it's so weird I can't actually feel it. That's bizarre. That's the reason why. Alright, so if it's walking on you, alright, so those are mechanoreceptors. The can has to be distorted enough, or the receptor has to distort enough that ions are able to move through the gate. If the ant doesn't compress those receptors enough, it stays shut. Okay. So, if the ant, let's say, walks on you, there has to be enough of a stimulus. There has to be enough touch receptors which are stimulated in order to generate enough of a response. They can be just by one, but just stick with me for this example for a minute. Let's say if it were super light pressure to the point that you can't feel it. Does that mean that your resting membrane potential of that touch receptor is negative 70? No. Nope. What happens if it reaches negative 65? Ooh, I'm getting closer. But did I reach negative 55? No, because remember, when I had mentioned negative 55 is threshold. As some people call it, negative 50, negative 55, negative 60. There's a range depending on what the cell is, right? But negative 55 is by far the most quoted, right? This is threshold. At negative 55, there's a structure right here called the axon hillock, or it's trigger zone. That's what generates the nerve impulse down the axon, right, at negative 55. If I'm at negative 70 to begin with, if an ant's crawling on me and the receptor reaches negative 65, did I reach threshold? Nope. Was an action potential generated? Nope. Something was generated. Something called a graded potential. Small fluctuations in the charge is something called a graded potential. When there's a huge swing in the charge, remember how I mentioned that at threshold, that's when those voltage keyed gates, those voltage gated channels, right? At negative 55, that's when they open, and the ion, remember the most abundant extracellular ion we talked about, sodium, floods into the cell. I don't know what the hell's up with that line right there. Floods into the cell. If sodium floods into the cell, sodium super positive. What the? Alright, ignore those lines. Sodium is positive. If it floods into the cell, this negative 55 generates the action potential, and the charge of the cell reaches somewhere right around as high as positive 30 millivolts. Right? So that's how high of a charge, that's how positive of a charge the cell actually receives or achieves once it depolarizes. Is positive 30. So here, we're going to look at the junction, the union here, between these two particular neurons. It didn't only have to be these two neurons, right? It could have been this neuron, and it could have drawn a muscle cell. Right, but just to stick with nervous tissue, let's just say this neuron to this neuron. Cool. This example, this takes into account, we see ligand gated examples of ligand and voltage gated channels. We don't see an example of mechanically gated channels, but that's okay. So the nerve impulse. Bolt of lightning? Not very good. As the nerve impulse travels through the axon. Remember how I mentioned when the cell at rest was -70? When the cell depolarizes, it swings all the way to +30. Down here we see these voltage-gated calcium channels. Yeah, they're voltage-gated. Means they're keyed by the voltage. So once the voltage hits, or once the charge hits the appropriate voltage, so once this nerve impulse comes down through, once it goes from -70 and makes the swing to +30, that's what then opens these channels. And these channels specifically allow calcium in. They don't allow sodium in, they don't allow potassium in, they don't allow magnesium, they allow calcium. That's my design. I am to allow calcium. So calcium gated channels open, calcium floods into the cell. Cool. There's an example of your voltage gated channels. Awesome. So that causes the exocytosis of the neurotransmitter. It gets kicked out. Awesome. That neurotransmitter then binds to its receptor on the subsequent neuron. Let's just call it acetylcholine. Let's call it dopamine. Let's call it dopamine. So dopamine is released from this axon, this synaptic term, the synaptic end bulb. Dopamine then goes and binds to its receptor. When that happens, this chemically keyed channel, or this ligand gated channel for dopamine, opens up. Now, it's not one thing that's kind of interesting when we think about it. It's not like dopamine, for instance, opens up this channel and then dopamine floods in. No, that's not what happens. Dopamine's the key. That chemical is the key. Right? I'm the gatekeeper. I'm the bouncer, or I'm the door. I'm the bell. I'm the door hop. Door hop. Bellhop. Doorman. Doorman. That's the one I wanted. I'm opening the door for you. Right? If I'm dopamine is the doorman. In this example, dopamine is the doorman. Dopamine inserts the key, opens the gate, just like the doorman opens the door. Does the doorman then go inside of the hotel? Nope. Stays right there. Opens the door and then shuts the door. That's dopamine. Again, for this example, dopamine binds to the receptor, opens it. That allows sodium to flood in. Dopamine doesn't then enter into the cell. Nope. Dopamine's just where it's supposed to be. Does that make sense? I think it does. I think it makes a lot of sense. So, anyways. So we see not all fluctuations in charge create an action potential. What are some ways we can arrive to an action potential? So a minute ago I had mentioned how if an ant or something is crawling on you, do you always feel it? No. No, you don't. Sometimes there are small fluctuations in charge. Like here. One of the things is that neurons something called summation, right? Something called spatial summation. If we have, for instance, when you make a fist, if you make a fist, it's not like your brain just one time sends one impulse to the muscle of your flexor digitorum and you boom, make a fist. Nope. It may have taken several, it has taken several impulses repeated bombardment in order for that muscle contracture to stay sustained. So for this example here, now we have been just talking about kind of like one on one. If only it were that straightforward, right? And I alluded to this last presentation. That is an unbelievably simplistic view of nervous tissue. Right? There are often hundreds, if not thousands, if not millions of synapses and networks between these different neurons, right? So if you were to take one neuron, right, in the brain and spinal cord, there is often hundreds, if not thousands, of different connections to that one particular neuron. Right, so the idea that, using the example of just one-to-one, it simplifies the example, but right, don't think that that is how simple it is. No, it is not. That's not how simple it is. It is merely simplified to kind of help you grasp the concept. So one of the ways that we can arrive to, again, an action potential. Remember, the action potential is generated when the cell depolarizes. Meaning once the cell crosses threshold, it depolarizes. That's where sodium, we just talked about a second ago. Sodium floods into the cell. The cell goes from -55, swings to +30. That process was depolarization. What it generated was the action potential, or that nerve impulse. Same thing. Cool? Alright. So here, let's say, alright, so one impulse, what if this one neuron, let me get this stuff off the screen. And this one neuron, if this one neuron here sent an impulse. Alright, so here. So this red neuron here, its charge is -70. Awesome. If neuron number 1 sent just a weak impulse, right? It was a weak gradient potential, and it changed. It was measured at +5. So -70 goes to -65. Well, did it reach threshold? Nope, it didn't. So did neuron number 3 generate an action potential? Nope, it didn't. Yeah, crap. Okay. So what do we do now? Well, if we have multiple neurons, let's imagine this one here changes to +5. So now we go from -70 to -60. Let's imagine there's a third neuron. Well, that third neuron, well, now that's enough, right? Because that's +15. If I take -70, add +15 to it, now I reach threshold. So spatial summation is when you have multiple neurons, right? And their potentials add together, right? For instance, if we add together 5 + 5 + 5, that equals +15. Well, -70 and a +15, that gives us -55, which is threshold, which we then, right, what happens at threshold? Those voltage gated sodium channels swing open, sodium floods in, and the charge swings to, call it +30-ish. Alright. That's when there's multiple neurons. What if it's just one? Right, that's the thing. That depending on where we are, sometimes that will happen. Right, if we talk about certain aspects of like the dorsal root, right, the entering into spinal cord, certain interneurons. So sometimes it is just that kind of straightforward. But more times than not, it is not. Right? Well, what happens if this one neuron, right? If each generation of an impulse, or each generation of a potential is only +5, well, that means this only goes from -70 to -65. Okay. So when that happens, when it teeters back and forth, right, when it goes from -70 to -65, it's not like it just immediately goes back to -70. Right? Ions, they move in unbelievably quickly, but it does take, right, fractions of a second for those ions to leave the cell, right, for those sodium ions to leave the cell. As the sodium leaves the cell, it returns the resting membrane potential back to -70. Cool. What happens if this, like, one neuron sends a bunch of impulses, like one right after another, after another, after another, after another? Well, now that -70 really quickly goes to negative. Okay, that's just obnoxious. Right. So because of those repeated multiple stimuli, just like you see right here, right, they're fast enough in succession that the membrane potential can't return back to -70, so it continuously climbs and eventually reaches threshold. That's one of the things that graded potentials can do, is they can summate, or they can add together. Right? You can add them together to reach an action potential. Right? Those graded potentials can work together to summate, add together, and then cause the action potential to occur. So, cool. When that happens, alright, so that action potential is generated. Cool. How does that action potential then actually travel down the neuron? How does it actually travel down? Remember that part of the neuron called the axon? Right. A couple ways. Something called continuous conduction, or there is something called saltatory conduction. So look at continuous conduction. With continuous conduction, it occurs much more slowly than does saltatory conduction. Right? Remember these sodium channels? Again, these are voltage channels. As the threshold is reached, the axon hillock, this guy right here, generates the action potential. And as that happens, right, that change in the charge begins to open up all of these channels. Well, each particular step along the axon, right, every channel has to open in order for the signal to continue down. So it occurs much more slowly. Much more slowly. Right? When we compare it to saltatory conduction, do you remember? Of course you do. Last class, when we looked at something called the nodes of Ranvier, remember the myelin sheath, that was that phospholipid layer which surrounded the axon. Whew, further back than I thought. That's alright. Here. Right? This myelin sheath which surrounded and encoded the axon. Right? I get these little hot dog bun looking things. I mentioned last week how that helps to propagate the signal. I mean, that's what helps to increase the speed of the signal, right? Of that nerve message. Now you might say, well, it's kind of stupid. Wouldn't you want all messages to be received as fast as humanly possible? No. Right? Our brain is bombarded with millions of impulses every single second. Some of them are not nearly as important as others, right? Pain, for instance. Right? Pain is carried by nociceptors. They're C fibers. They're very small, and they are unmyelinated, meaning those neurons which transmit your sense of pain are amongst some of the slowest in the body. Right? There's different reasons as to why that is. Right? As much as I love to digress, I'll spare you. Because of the presence of the myelin sheaths, there's a space in between them. Here. That's where sodium can flood into the cell. Sodium can flood in here. Sodium can flood in here. Flood in here. Flood in here. So when that happens, right, that electric current is carried, it jumps from one node to the next, from one node to the next, from one node to the next. Right? It doesn't have to, that action potential isn't carried and doesn't cause every single sodium receptor to open like it does in continuous conduction. Right? With continuous conduction, remember, every single one of these sodium gates had to open. That doesn't have to happen in saltatory conduction, and the reason why that is able to occur like that is because of the presence of the myelin sheath. Right? The myelin sheath only allows certain sodium receptors to open up, because those receptors, which are in essence blocked by the myelin sheath, don't have to open. Right? The other thing that the myelin sheath will do, it helps to, think of it kind of like prevent arcing. Right? Wires. Even if you've never done any electrical work in your life, you have undoubtedly seen some sort of show or movie where somebody has defused a bomb. Right? They see a bunch of wires. You're like, oh God, I don't know which one it is, and they magically cut the correct one to stop the bomb. All right. Well, the wires are coated in this kind of plastic rubbery stuff, right? Latex, whatever it is, something which doesn't conduct electricity. And why? Because when any sort of current travels through wires, those wires don't actually need to touch, because that current would actually arc from, if the wires got close enough, it would arc from one wire to the next. Think of the spinal cord. Think of these nerves. Think how close and how densely packed these neurons are. Right? Certain conditions like multiple sclerosis, right, actually causes scarring of the myelin sheath, right, in the central nervous system. Right? So it's not so much the axon or so much the neuron per se, but it's the myelin sheath itself. The myelin sheath gets scarred and doesn't function like it's supposed to. Well, if the myelin sheath, which is meant to help control signal conduction and the speed in which it takes place, if that's all of a sudden, imbalanced, or if there's some degree of problem, that's where then they have some of the problems for people who have MS, right? Walking difficulty, ataxia, those sorts of things. So neurons, obviously, they travel along various highways or tracts, but what do some of those networks look like? Right? Yes, we talked about, right, how neurons enter into the dorsal root, and from the dorsal root into the dorsal gray horn, then from the dorsal gray horn into the white column, and then from the white column all the way up to the brain. We talked about those, but the actual highway inside of it, what do the actual lanes look like, or what do the actual what do the actual lanes look like? And you can see, right, there's a few different styles. There's something called a diverging circuit. Right, you can see input. Right, there's a much greater amount of output than there is input. Right, so we talk about right. Actually, what I'm going to do is to kind of show you the examples of all four of them. Right, for first, and I think it'll make it a little bit easier to kind of understand them. Right, so we see diverging circuit. Then we have a converging circuit, reverberating circuit, and then parallel after discharge circuit. So when we talk about a diverging circuit, think about the input. So we think about the input. Right. Remember how I mentioned it in the last presentation, I mentioned it just about 4 minutes ago, how there are, right, generally not one particular neuron generates, or generates not only one neuron to one neuron, right, or it's not one neuron to one particular cell. Sometimes that's the case. When we talk about a motor, something called a motor unit, right? You would have talked about these again in chapter 10. But when we look at a motor unit, that is one neuron, right? And all of the different muscle, or all the different muscle cells that it then goes to control. So you're going to think about a motor unit. Ooh. Try to do that quickly. A motor unit. Motor unit, there's one neuron. So one neuron. And then here it's just showing it going to only two motor neurons. Right, that's the output. Remember, output is the motor component. Right, a neuron, you never have, for instance, output from the brain carrying sensation. That doesn't make any sense. It's sensation which travels to the brain. Right, so therefore the brain knows what motor response to control, to carry out. Right, but that one neuron and all of the individual muscle cells, right? So that one neuron might go to 50, 100, or 1,000 different muscle cells. A converging circuit. This is how there's so much sensation which goes into every little thing that you do. From what's a good example? The brain stem. Last class we talked about the medulla and how that is a cardiac and respiratory reflex center. Well, how is it our medulla knows how to increase cardiac rate, for instance? Well, inside of the carotid arteries, there are baroreceptors which stretch and they send impulses into the medulla. Alright. Inside the kidney, there's different hydration receptors which send impulses to the medulla. Awesome. Inside of the mouth, you have different osmoreceptors which further detect the level of hydration. Right? So that's an example of how you have multiple tiers or multiple steps of sensation eliciting a single motor response. Right? That one motor response would be, okay, increase cardiac rate. Right? So the converging, how you have multiple sensations all coming together to elicit one motor response. Reverberating circuit. This is a couple of examples. Right? These are things which kind of beget themselves. You're like, huh, okay. Right, when we think about a reverberating circuit, this is the thing which begets itself, right? This particular neuron. You can see it goes and, let's say, it attaches itself to what muscles of the flexor digitorum. Cool. When I make that fist, when I make that motor movement, right, my brain caused that to occur. Awesome. At the level of the flexor digitorum, right, let's just say I keep on making my fist. I keep on making my fist. I keep on making my fist. Does my brain just have to continuously, repeatedly send impulse after impulse after impulse after impulse after impulse after impulse? Not necessarily. It can't just send one impulse and be done. The brain does have to put input, but just bear with me for a second. Right? The brain does not have to send an impulse every single second because of the fact that there are reverberating circuits. Meaning, once this neuron was stimulated, guess what? It is going to continuously stimulate itself. Right? Follow me? So, neuron stimulated. Alright, it stimulates, let's say, the muscle itself, and then it stimulates these sensory neurons here, which then, or I'm sorry, these, they may not specifically be sensory neurons, I apologize, but these interneurons here, travels up, stimulates this interneuron, which then in turn stimulates this motor neuron. Well, that motor neuron then turns around and stimulates this interneuron again, and that cycle continues. Right? The brain can then send an inhibitory impulse, meaning it stops this initial signal from occurring. Alright, so if it stops that signal, alright. Okay, the problem is the cycle's still occurring though, and that's the thing. That's where yeah, you're ready for it. Not all impulses, right? Just the same as how your brain can cause a function, your brain can also inhibit the function. Right? Just like your brain can actually cause muscle to move, it can inhibit muscle to move. And it's all dependent upon what chemicals are released. Certain chemicals are excitatory, meaning they're going to cause a muscle movement to occur. Some chemicals are inhibitory, meaning, I'm going to prevent a muscle movement from occurring. Right. Another example of reverberating circuits. This is, again, those people who have, for instance, like an actual muscle spasm. Not like, oh, I got a little bit of a Charlie horse. Like, I mean, that is a little bit, but when we talk about muscle spasm, right, that's also another example of a reverberating circuit, because that muscle, as it contracts, guess what? It is just continuously causing itself to contract. Right? This muscle contracts. Awesome. That motor neuron stimulates this interneuron, which stimulates this interneuron to stimulate the motor neuron, which then just continues on and on and on. Right? So that's just another example of where these kind of cycles can take place. Right. Now, this is, we talk about parallel after discharge circuit. You're like, okay. Aside from having a horrific name, right? Certain reflexes, right? For instance, when I mentioned how our brain is not made aware of every single thing that takes place. Right? So no, it's not possible. one of the ways, so this parallel after discharge circuit, what that essentially, what this allows for is for the impulse to be delayed. Right? Like let's imagine if I had 3 different people giving me directions on how to get somewhere. I'd want to make sure I got all 3 pieces of information at the same time so I can then make the decision. Right? If person A tells me, hey, take the Tappan Zee Bridge. Awesome. I'm going to hop, and I start hopping on the Tappan Zee Bridge. And then the second person says, make sure you avoid the Tappan Zee Bridge because it's all backed up, take the George Washington. It's like, well, no, what the hell am I going to do? Right? A second ago, how I talked about there are, right, with converging circuits, there are so many different, right, sensations and stimuli which go into making just one single decision for the brain. Same thing here. Right? With a and you predominantly see this in reflexes. Right? Reflexes are initiated outside of the brain. Initiate the reflexes, right? Spinal reflexes, for instance, are initiated in the spinal cord. Right? That's not to say that the brain can't influence them. It can, and it does. Right? But one of the functions of a spinal cord reflex is that it is as quick, as fast as possible, and it occurs without the brain's input. The brain's still involved. The brain is cued in with what's going on. Right? But right, this action can actually take place before the brain, right, before the brain has to provide input. Does that make sense? Alright. So we kind of went through the whole course, the whole tract of, right, looking at nervous tissue, following it from point A to point B up to the brain, and then from point B back down to the body. We've looked at what actually originally generated that action potential, right, and what were some of the influences of that. Now we're going to look at, right, just some of the different structures, some of the different kind of more specialized features of the brain. Excuse me. So this here, right, this is actually that kind of blue model. That's something that's deep inside of the brain, in the middle of the brain. Those would actually be hollow well, they have fluid in them, but that would be an empty space. Let's imagine if I drained all the fluid out of the brain, those would just be empty chambers. Right? They're not called chambers, they're actually called ventricles. Right, so literally, right, there's a ventricle which is kind of like C-shaped, it's got a little bit of a tail. Right? Those are called the lateral ventricles. The lateral ventricles. Right here in the middle, that's something called the third ventricle. The third ventricle. The wall of the third ventricle is the thalamus. Right, the wall of the ventricle is the thalamus. Right. This here, something called the cerebral aqueduct. So these ventricles are full of something called CSF, something called cerebrospinal fluid. A couple of functions: eliminate waste, provide nourishment, provide protection. It's produced inside of these ventricles. Right? And this CSF eventually flows down the spinal cord and encompasses and encapsulates and it encircles the brain and the spinal cord. So that's why you see it's produced in the ventricles, but there's these different aqueducts, right? The cerebral aqueduct, for instance, right? The interventricular foramen, right? Freeman and Monroe, Freeman and Magendie, those aren't all identified here. But there's different openings for this CSF, this cerebral spinal fluid, to be able to exit the brain and the ventricles. Alright, so up here, lateral ventricles, right, third ventricle. As I travel down between the cerebellum and the pons is something called the fourth ventricle. Something called the fourth ventricle. And then from there, as we continue downwards, eventually it opens up into the central canal. Remember the central canal? That was that hole which then, you know, kind of pierced down through the gray commissure of the spinal cord. So, if we take the brain from a horizontal cut, right? If I cut the brain or cut the top half of the head off, looked straight down, this is what I would, you know, see. And you can kind of envision how this is C-shaped, right? Again, the C, we're looking at kind of half of the C. But some things we can see. Again, this is the lateral ventricle right here. There's this line between, right? There's this connective tissue. There's this bridge. We looked at this last week. Something called the septum pellucidum that separates the left and right ventricles, right? The left separates the lateral ventricles into a left and into a right. Right? When we look at this here you can see it really well. That's something called the choroid plexus. The choroid plexus. The choroid plexus, that's what's actually going to produce the CSF. That's what's actually going to produce the cerebrospinal fluid. Again, that's the choroid plexus. The choroid plexus, again, that's in all the ventricles, lateral, third, fourth. Right, so it's not only in the lateral ventricles, it's just where you happen to see it in this particular image. Right. But one of the things, right, that we're looking at here, it's produced in the ventricles. Awesome. And then travels down, right, through lateral ventricle, third ventricle, down through the cerebral aqueduct, the fourth ventricle, down through the central canal. And you can see how it comes up and it surrounds the spinal cord. It also continues upwards and surrounds the brain. Right, and most of these things we pointed out, right, corpus callosum, we pointed that out, interventricular foramen, right, hypothalamus, right, the choroid plexus, right, these different, you know, the pons, the medulla, a number of these structures we've already pointed out. Right, a number of these other ones we're going to point out here in just a second when we get to the next image. But one of the things to pay attention to is, right, where this fluid is. You can see it surrounds the brain. It surrounds the spinal cord. Right, when people get a spinal tap, right, when they have this CSF drawn off, remember it's done at around the level of L3, L4 because there's no spinal cord at that level. Right, so when people have, you know, this fluid removed for testing purposes, let's say they're trying to test meningitis or something like that, right, this, people can have that kind of rebound, you know, spinal tap headache because you've now just removed a huge amount of fluid from the CSF. Now CSF is continuously produced, absolutely, but still, you draw some off, it can definitely cause problems and headaches, amongst other things for sure. When I had mentioned how, right, the cerebrospinal fluid is continuously produced, yeah, it's continuously produced. Right, every 8 or so hours, there's a whole fresh batch of this stuff. So because of that, there's got to be a way to reabsorb this stuff, and there is. In the top portion between the left and right hemispheres, there's something called the superior sagittal sinus. That's where these little tiny villi, little finger-like bundles of blood vessels, can reabsorb that fluid. They can reabsorb the CSF. Right? Well, not the fluid portion of the CSF, right? I don't want you to think that, oh, CSF is getting dumped into the bloodstream. No, that's not correct, right? The fluid portion of the CSF is being reabsorbed. Right? When it doesn't, right, let's say there's some sort of blockage, some sort of infection, something, tumor, whatever, that's where somebody can develop hydrocephaly, right, water on the brain, where the brain starts to, or not the brain, but the frontal bone or the various cranial bones begin to kind of protrude, especially the frontal bone, because of the increased fluid accumulation within the skull itself. So one of the other kind of layers, right? So we talked about this CSF. Something else with the brain, something called the meninges. Now the meninges, they surround both the brain as well as the spinal cord. Right? I unfortunately don't have the image of that right here, but we did see it last week on the first presentation. But here, the brain, right? Here's the bone. It's been removed, obviously, so we can now expose the brain itself. This kind of hazy, right, hazy-hueish layer, that is the arachnoid matter, or the arachnoid mater, however you want to pronounce it. It goes in order: dura mater, arachnoid mater, pia mater. The dura mater is very, very thick. Right, here's the bone. The first mater you would go through is the dura mater, right here. Very thick, dense covering of stuff. If the dura mater was left intact, you wouldn't be able to see any of the gyri and sulci that we see. None of them whatsoever. Alright, so dura mater. Right here. Cool. Beneath the dura mater, or deep to the dura mater, again, there's a subdural space. Right? But when we look at the next layer of the meninges, again, that's the arachnoid mater, this kind of whitish hue. Right? You can see it over here. You can see the discrepancy a little bit better. Right? All in through here is all arachnoid mater that we're seeing. The pia mater, you look at this, you're like, I don't really see anything. And it doesn't look like you see anything. And the reason why that is because the pia mater is adhered directly to the brain itself. Right, directly to the brain itself. Right, actually, I think on this last. Yep. So here's the cortex of the brain. This reddish, this reddish layer. Right. So when I say, right, the pia mater is adhered directly to the brain, it is literally adhered directly to the brain itself. Right. Almost like your skin is adhered to you. Right. You're not removing your skin from your body. Next, right, we are going to get into the vasculature of the brain. Right, this is just kind of a brief representation of how vasculature the brain itself is. The brain receives a huge amount of blood supply. Right, it needs to. It's what blood vessels. Right, we can see right down through here. Right, the carotid arteries. Now there's the common carotids, which come off of either the brachiocephalic or the aorta itself, right? But either way, as the common carotids ascend, as they go up towards the head, they bifurcate or split into an internal carotid and an external carotid. The external carotid stays external to the head. Right, so we're not going to look at that. We're going to talk about the internal carotid. Right here, we see the internal carotid right here. That, in conjunction with the vertebral. The vertebrals come up, and the vertebrals actually give rise to something called the basilar artery. That's this guy right here. The internal carotids come up and actually continue on with something called the middle cerebral artery. If we look right here, it kind of forms like this circle. Oh yeah, look at that. Right here. It's something called the circle of Willis. Right, right? The circle of Willis. This essentially is what kind of gives all the branches, gives rise to all the different branches which go to feed the various parts of the brain. Right? The basilar artery, right here, gave rise, or was arisen from the vertebral arteries. Right? The basilar artery feeds, again, in large part, the brainstem. Right? The pons. Right? For the most part. As we come up, right, the middle cerebral artery, right, these little nubs here, yeah, that's the internal carotid arteries, right, the anterior cerebral arteries here, right, anterior cerebral, posterior cerebral, we don't really see those, but these would be here, and they correspond with what area of the brain they then feed, right. For instance, the posterior cerebral feeds the posterior part of the brain, so like the occipital lobe. So people who had, for instance, a posterior circulation stroke would most likely have some sort of issue seeing. Perhaps they would even have some sort of balancing issue because the cerebellum is also fed by the posterior cerebral artery. Right. So if somebody has a middle cerebral artery, again, that generally feeds the middle portion of the brain. Or as like the middle, kind of, if you just take your hand, and kind of just lay it like just as if you're gonna like, oh, I'm so bored, I'm just gonna rest my head in my hand, right from the side. That's the area, right, that the middle cerebral artery feeds, right. Anything from ataxia, movement issues, speech issues, etc. So because of how vasculature the brain is, something else that has to be taken care of, something that has to be, cautious of, is the sensitivity of the brain to a variety of different chemicals or a variety of different toxins, for instance. Because of that, that's where the brain has something called the blood-brain barrier. The blood-brain barrier, again, that's achieved via astrocytes. You see glial brain cells support the barrier. Yeah, those specific glial cells are the astrocytes. And you can see how they form this very, very tight junction surrounding the blood vessel. Now, here's where we're going to get to specialized nerves, where specialized nerves will exit and enter the brain directly. Yep, that was a little bit of a grammar issue, right? But there are some nerves which are going to enter and exit the brain directly, right? They don't go to the spinal cord, they bypass the spinal cord, they exit the brain directly, and they re-enter the brain directly, right? For the most part, right, really in large part, these nerves deal with autonomic function, right, GI function, heart rate, breathing rate, etc., as well as your special senses, right, touch, not touch, taste, hearing, vision, smelling, right? But I'm actually going to cut this one off here, and I'm going to pick up on the next presentation, continue this presentation with the next video.